Excuse me. Okay. All right. Well, welcome to this tutorial on OpenGL Mathematics, the GLM library. What we're going to do is I went to the website, downloaded the file, unzipped it here, took a look here at what it's looking for, and it's looking for the GLM directory, which is actually inside a GLM directory. So it's looking for this GLM HPP file. Okay. So I'm just gonna, and it's also looking for GTC right there, the matrix transform HPP, and the type pointer HPP. So we're gonna take this GLM directory, just the whole thing, copy it into one of our projects. Directories OpenGL Live Inc., which is where I've been putting everything, paste it in there, copy it over. Okay, so now we have GLM, and all that. So let's see if we can actually get this to, first of all, include those files. Let's go to the top. And I've already done some work, and I should probably make this one of my 5th or 6th videos. And I'll put the videos in order later, but for right now, we're going through the Chapter 8, by the way. Chapter 8, which is about transformations in that learnopengl.com tutorial series. Okay, so first let's put in the GLM stuff. Okay. So the first one is GLM HPP. And I like how this actually, that's so cool. That's cool. So GLM, so it goes with, yeah, weird, okay. And that's because, I wonder, just because I wonder when I wonder. Let's go into here. I don't want to really complicate my include directories because I love having just this one. So I'm not going to wonder about that. Never mind. So now we can go include GLM, GLM, GTC. What was it? Matrix transform. Yeah, there it is. Okay, and then the other one was GLM, GTC, type pointer. TR, there we go. Okay, great, so that gets included. And it says OpenGLM is a header-only library, which means that we only have to include the proper header files, and we're done. No linking, and compiling necessary. Well, before you actually do, they actually come out. GLM can be downloaded from their website, which I did. Copy the root directory, the header files into your includes folder, and let's get rolling. Okay, so I've already been rolling, so that's good. Okay, let's see if we can put our transformation knowledge to good use by translating a vector of 100 by 110. Note that we define it as a GLM vec4 with its homogeneous coordinate set to 1, so that's homogeneous coordinate right there. Okay. So there's the vector, there's the translation, there's that, and that. What have you got there? What have you got there? Okay, so it goes through all this. Together, the translation makes a multiplier and output the result. So then they describe what they're doing, which is interesting. And let's do something more interesting and scale or rotate a container. Let's do something more interesting and scale and rotate the container object from the previous tutorial. That's where I want to start. First, we'll rotate the container by 90 degrees counterclockwise. Then we will scale it by 0.5, thus making it twice as small. Let's create the transformation matrix first. Okay, first we scale the container by 0.5 on each axis, and then rotate the container 90 degrees around the z-axis. Note that the textured rectangle is on the xy plane, so we want to rotate around the z-axis. Okay. Rotate, transformation, 90 degrees around the z-axis. X, Y, Z, translate. Scale the container by 0.5 and then rotate 90 degrees around the Z. Note that the textured rectangle is on the XY plane, so we want to rotate around the Z-axis because we passed the matrix to each of GLM's functions, right? The matrix. GLM automatically multiplies the matrices together. So this transform is getting multiplied by this matrix that's getting sent, which is 90 degrees, 0 degrees, 0 degrees, and then 1. So that's, yeah. And then the scale trans times the vector 0.5, 0.5, 0.5. And then apparently the W, or the homogeneous coordinate, is left off. Or how does the rotate work? Did it already tell me how the rotate works? How does the rotate function work? Because I could be describing it incorrectly. Okay, and so we're already at the end. Let's just go to the website. Where is it? I just want to look it up real quick. GLM rotate. GLM rotate vector. Where is it at? Where's the GLM website? Let's just go to their website. You can locate it here. API documentation. OpenGL mathematics. This is not the API documentation. The manual, there's a manual. Alright, let's load the manual. How many pages is the GLM manual? Oh, that's not bad, 36 pages. Oh, the pretty flowers at the beginning and the... Oh, the funny looking duck. That's like me. Look, how do I do this OpenGL stuff? Okay, so let's see. Rotation, rotation, rotation. Da, 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 da. Code samples. Isn't there like an exhaustive reference? Don't think that's going to be available in 36 pages. Okay, well that wasn't helpful. Let's go back. So where is the reference? Related pages, modules. Oh, probably modules right here. Common functions, vector relational, angle and geometry. Still not showing me. Could it possibly be more cryptic? Main page. Related pages. Differences between that and that. To-do list, modules, extensions, rotate normalized axis. That just doesn't look like it. No, it doesn't. Welcome to the world of programming. Glad I already have a good job. Not programming. Namespaces, huh? Let's go to namespaces. Here's a list of all the documented namespaces with brief descriptions. Okay, that's a great list that goes on and on and on. It means absolutely nothing to me at this point. Files. Okay. All right, hold on. Let's go back and look at this again. And I'm already lost. I'm so lost. Okay, so GLM rotate. GLM rotate. I know I googled this before, and it's insanity to do the same thing over and over and expect a different result. But duh, there's the function. That's exactly what I was looking for. Why didn't I just click on, I don't know, the first Google result? Okay. So it is the angle and then XYZ. So they're also leaving out right here. Whoops. Right here. So there's the matrix, right? Rotate. Oh wait, that's not even the one. I think it's this one. Rotate, yeah. That looks like a template thing, but anyways. So it's the matrix, then the angle, and then XYZ. Which would be here, matrix, angle, XYZ. Transforms a matrix with a rotation 4x4 matrix created from an axis of 3 scalars and an angle expressed in degrees, which is exactly what this is. Because that's in degrees. Or wait, see, it keeps... Isn't that great that Edge just keeps doing that? I wonder if it would do that if I went back here, and I go back. Yeah, so Edge is just like freaky. Is that like the top of the page or something? So Edge goes to the top of the page if you go somewhere else, and you just, yeah, okay. And then it even goes to a whole nother page if I do that and come back. Oh, that's just great. Okay. The next big question we get to, okay, so anyways, so there's the matrix. That's an angle, and it's not actually your x coordinate, because I was thinking maybe this is y, z, and w. So actually rotate 90 degrees, x, y, z. So that must be, yeah. So that must be, oh gosh, why does it do that? So that must be like this 90 degrees. Going here rotates 0 around the x. Going here, you rotate 90 around the y, or 0 around the y. And then here, because it's 1, it rotates 90 degrees around z, because that's why he says they're going to rotate 90 degrees around the z-axis. Okay. All right, I'm just wanting to understand, so... Okay, so back to what we're doing. Let's do something more interesting. Scale rotated in the previous tutorial, blah, blah, blah. First, scale the container rotated. Note that the textured rectangle is on the XY plane, so we want to rotate around the Z axis. Okay, good. Because we passed the matrix to each of GLM's functions, which I just looked up, and it took me about probably 4 minutes. GLM automatically multiplies the matrices together, resulting in a transformation matrix that combines all the transformations. Okay. So you start out with an identity matrix, trans equals rotate trans, trans equals scale trans. Okay. Some versions of GLM take the angle in radians instead of degrees, in which case you can convert it to radians with a GLM radians, whatever. The next big question is this: how do we get the transformation matrix to the shaders? Aha. We shortly mentioned before the GLSL also has a matrix 4 type. That's the GL shader language. So we'll adapt the vertex shader to accept a matrix 4 uniform variable and multiply the position vector by the matrix uniform. So the position vector, GL position, equals transform times vector 4 position, comma 1. Aha. But then we'd also have to see, because we create this, we'd have to tell it, okay, that's probably next. GLS also has mat to a method has not for swizzing up, just like we do that for measurement. A lot of the major, especially sure explain what's happening. Okay, blah blah blah. We added the uniform and multiplied the position vector with the transformation matrix before passing it to GL position. Our container should now be twice as small and rotated 90 degrees, tilted to the left. We still need to pass the transformation matrix to the shader. Right. So GLUint transform loc equals get uniform location, our shader transform. So that takes from the shader's compilation and that variable transform, and it puts it into transform location, which is like the address of the variable within the memory block on the shader. Cool. Uniform matrix 4v uniform, and then this is the post fix or whatever they call it. Yeah, post fix. Transform location 1 GLM value pointer trans. Right. So this takes the pointer for trans and sets it right into the shader. Interesting. We first query the location of the uniform variable and then send the matrix data to the shaders via GLUniform function with matrix v4 as its postfix. The first argument should be familiar by now, which is the uniform's location. The second argument, the uniform's location. Wait. Oh, right here. Okay. The second argument tells OpenGL how many matrices we'd like to send. One matrix. Oh, so you could point it to like an array and specify how many members in that array. Wow, that would be interesting. The third argument asks us if we want to transpose our matrix, that is, swap the columns and rows. OpenGL uses an internal matrix layout that's called column major ordering for their matrices under the hood. GLM already defines its matrices using column major ordering, so there's no need to transpose the matrices. We can keep it at GL false. The last parameter is the actual matrix data. Well, it looks like it's a pointer to the data, but GLM stores their matrices not in the exact way that OpenGL likes to receive them. So we first transform them with GLM's built-in function value pointer. Value pointer. Oh, so trans. Okay, so whatever that does, whether it's a pointer or the actual, yeah. Anyways, we created a transformation matrix, declared a uniform in the vertex shader, and sent the matrix to the shaders where we transform our vertex coordinates. The result should look something like this. Right, okay. So what did I do? Oh, that's right. And I've got the 2, so actually, can we do this to just 1? I bet you we can. Let's see. So, okay, we'll back up. We'll go even slower. Even slower. Okay, right here. Okay, let's create the transformation matrix. So let's just put this in there. Boom. And just for reference, source code, vertex, fragment shader. Okay. So are we creating this matrix within the main loop, or where are we doing that? Oh yeah, it's right down here. Where is it? It's actually right after, okay, activate shader, create the transform right in the main loop here. This is so loopy. It's so loopy. Okay, so there's my loop. Activate shader. Okay, why does it do that? Why does it do that to me? Okay. Create our transform. Transform. So GLM map for trans. Trans equals GLM rotate, blah, blah, blah. Scale. Okay. Did we break anything? No, it actually worked. Okay, so that's fine. So I don't think we need that stuff anymore. So we added the uniform. Okay, where are we at? We created a transform matrix. Declared a uniform in the vertex shader. Ah, yes. So, and I forget where our vertex shader is and what it's called and all that stuff. Vertex shader, vertex texture dot text. Okay. Projects. What's this project called? Open what? Soil trial right there. There it is, vertex texture. Okay, so now we just go into here. Ba-da-ba. Looks like the only change is right here in position, because position comes down, and so the uniform gets multiplied by, yeah. Interesting. So that's fine. And then save that. So that's the only change to the vertex shader, is we create the uniform, which we can connect to the app, and then transform gets multiplied by position. Okay. Okay. What else? Created a transformation matrix, declared a uniform in the vertex shader, and sent the matrix to the shaders where we transform it. Okay, so sent the matrix to the shaders, which is right here. And then incidentally, where does that get done? In the loop. It's all loopy. It's exactly right after the, wow. Dun, 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 dun. Okay, and then why does it have an issue with that? Oh, because it's spelled wrong. Okay, we're good now. So this is just the rotation and the scaling. Oh, and it works. Does it still do the... Oh, it does. That's so cool. Okay. If anybody doesn't know what I just did, the fragment shader is set up with two textures, two samples that are mixed together here based on a mix value. The mix value is also a uniform. And then the mix value is actually communicated to the shader down here. Here's the key callback, and we modified the key callback in a previous tutorial. So that I hit the down key, the mix value goes down to a set value of 0. If it gets the 0 key up, then it goes to 1 maximum. And it uses the mix function here in the fragment shader. And so the mix value determines how much of this and how much of that texture is mixed together on the particular set of vertices. Excuse me. And anyways, so yeah, I can't believe this rotation stuff worked. That is like actually really easy. So now I'm wondering, because so mix value, and then what if we see the transformation is right up here, and this is the degree that it's transformed. And it's scaled down. So what if we scale it the other way? Yeah, it's bigger. Okay. Okay, so how long have I been recording? Does it even say? 26 minutes. Okay, so let's see if we can do a little bit more before we end the actual video. So there's that. But it's not 90 degrees rotated, is it? It's like 45. Why is it 45? Why is it 45 degrees? What if it's 0? Set it to 0. Yeah, so then it's fine. So what happens if I put in 45? The heck? That's 45. And then what's 90? That's all the way around. That's 45 and 180. It's messed up. Not sure why. It's a little bit weird. Anybody else think that's weird? Okay, anyways, so let's move on. Then they use the time get time thing and they change it. Using the last transform on the container, try switching the order around by first rotating and then translating. See what happens. Try to reason why this happens. Try drawing a second container with another call to draw elements, but place it at a different position using transforms only. Make sure this second container is placed at the top left of the window, and instead of rotating, scale it over time. Well, I already do that. I do two particular draw elements. So, oh, you know, this is cool. So, I wonder. Because what this does, yeah, this is okay. Let me think. So if I can you do that? I wonder if I can do that. Let's see. Let's just see what happens. Maybe we'll break it. Okay, so right here, let's create a second transform. So GLM trans number 2 trans equals GLM rotate slow. What is rotate slow? Rotate trans number 2, and this one let's do 45 GLM Okay, so that should be fine. Trans equals GLM scale trans GLM. Okay, we're going to scale the other one to be small. Whoops. And then we already know the location, so we don't need to do that. Okay, so theoretically it'll change the rotation and the scale of the second cube. It did. Okay, so for interesting. Yeah, and the transformation. Okay. Interesting. Okay, so we're up to 32 minutes, and that is very good. I'm going to actually see, this could be quite good. What's the next chapter? Coordinate systems. Okay. Local space, world space, view space. Okay. Well, just with that right there, that gives you a 2D sprite engine. You can use that to make a 2D sprite engine. So that is very exciting. I'm going to work on that over the next couple of weeks here. And thank you all for tuning in. Whoever tuned in, leave comments and like and subscribe. And I will hope to get my channel to be more active here very, very soon and shortly. All right. And I hope this helps somebody. I hope this at least lift a few frustrations from OpenGL programming for some folks. All right, have a good day. Bye bye bye. Let's see here.